Okay, this is lecture 5 of this short course in Algebra and Number Theory. And today we're going to talk about Fermat's little theorem, primes and repeated squaring. Okay, so this is our overview of what we're going to do here in this session. So first we have Fermat's little theorem, which says let P be an odd prime, let A be an integer, and suppose that A is an integer such that P does not divide A. Okay, if that condition is satisfied, then A to the power of P is congruent to A modulo P. So I'm going to give you a proof of Fermat's theorem. I'll give you an equivalent statement in terms of groups. Then we'll look at two examples. The first one is showing that 221 is composite or not prime, and I'm going to use repeated squaring to do that. Then I'm going to show you an example of a pseudo-prime in base 2, which is 341. So this is an example of a not prime, but it passes this test. So in other words, that converse does not hold. All right, so let's get started on this. So I think I'll move this over to the right, and I'll just work here on the left. Okay, so we've got our statement. So now I want to start to prove this statement. So what we want to do is first note that since P does not divide A, we have the greatest common divisor of A and P is equal to 1. Right, so what this means is that A inverse exists in integers modulo P. All right, so now that we know that that exists, let's set out a set. Let S be equal to the set containing 0, 1, 2, up to P minus 1 in integers mod P. Okay, so multiplication by A, so we're going to multiply S by A, permutes S. Okay, and the reason it does that is because the GCD of A and P is equal to 1. So then, for example, so let's just put e.g., if we have P equals 7, and A equals 2, then 2 times 0, 1, 2, 3, 4, 5, 6, 6 being P minus 1 in that case. Okay, so multiplying this by 2, we get 0, 2, 4, 6, which is 2 times 3. 2 times 4 is 8, but that reduces modulo 7 to be 1. And then 2 times 5 is 10, but that's 3 mod 7. 2 times 6 is 12, which is 5 mod 7. Okay, so you can see that this is just a permutation of this set right here. So hopefully it's at least plausible for you at that point. Okay, so what we want to do next is take the product. So taking the product of all non-zero elements of S. Okay, so we have the product, and I'll use an uppercase pi to denote that product of all x such that x belongs to S without 0. Okay, now just looking at this, so that product is going to be p minus 1 factorial modulo p. Okay, and that's congruent to, looking at this from the other point of view, is if we multiply a in, then we have, and we take the product, we also have a to the power of p minus 1, because there are p minus 1 of those a's once we've multiplied them in. And then that's times p minus 1 factorial, and so this is also modulo p. Okay, so given that, now we need to notice that since GCD of p and p minus 1 factorial has to be equal to 1, because none of the numbers in this product here have a common divisor with p, because p is prime. And in that product, you haven't even got up to p yet, right? So the GCD must be equal to 1 there. Okay, so since we have that, p minus 1 factorial inverse exists. And so now what we can do is multiply that in our congruence here. And when we do, we get 1 is congruent to a to the power of p minus 1 mod p. Okay, so what's left to do then is to just multiply this congruence that we've obtained throughout by a. And so we get a congruent to a to the power of p. You can see my pen is running out of ink. Mod p. Okay, which completes the proof of our claim, or Fermat's claim. Okay, next, from the point of view of groups, let G be a group of order n. Then the order of the element G in that group divides the order of the group. All right, so in group theoretic language, we would write this G to the power of, let's say, m. So if this is equal to E in G, right? And so m, the order, so the order of the element G is least positive integer m that makes this happen, okay? So that's the element, the order of the element G. All right, so now in terms of Fermat's little theorem, what this says is that in the group, integers modulo p without 0 with multiplication, let's say the group, there are p minus 1 elements. Okay, p minus 1 is the order of this group, right? And so we see that the order of any element in this divides into divides the order of the group, right? But the order of every element is actually p minus 1. So every non-zero element of this group has order p minus 1, which is the order of this group here, right? Because we have a to the p minus 1 is equal to the identity, which remember in this group is 1, for all a belonging to integers mod p without 0. Okay, so that's a group theoretic point of view on Fermat's little theorem. Okay, now our next topic here is an example of Fermat's little theorem, which says use Fermat's little theorem with a equals 2 to prove that 221 is not prime. So what we need to do here is represent 221 in base 2, but I'm getting a little bit ahead of myself here. What I want to do, okay, so we want to set out 2 to the power of 221 minus 1, right, mod 221. We want to work out what this is and show that this is not congruent to 1. Because if we can show that, then we can show that 221 is not prime. Okay, so next thing I want to do is show you how big this number is, 2 to the power of 220. So you can see it's a fairly large number. So if it were much bigger, then it could overflow the memory of your computing device. So what you want to do instead is use a technique known as repeated squaring, so you don't overflow the memory of your device. All right, and this makes it simpler to do by hand as well. Okay, so back to this. What we want to do here is represent 221 in base 2. Okay, so basically 221 is equal to 1 plus 4 plus 8 plus 16 plus 64 plus 128. And you get this from expressing 221 in binary. Okay, and so now we want to then use the fact that 2 to the power of 221 must be equal to 2 to the power of this sum, but then using the fact that we can break this up as a product, 2 to the power of 1 times 2 to the power of 4 times 2 to the power of 8 times 2 to the 16th times 2 to the 64th and 2 to the 128 mod 221. Okay, so we start to calculate this. We want to make a table of these products, right? So 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 4 is 16. Next, we want to square this because 2 to the power of 4 to the power of 2 is 2 to the power of 8. So what we do here is we just square 16, right? So 16 squared, and we're working modulo 221, but when we square this, we get 256, which is 35 more than 221. So we say that this is 35. Okay, next we want to do 2 to the power of 16, but that's 2 to the 8th squared. And so squaring 35 and then reducing mod 221, we will get 120. Okay, next, 2 2 to the power of 32. We'll square 120 and then reduce modulo 221. So we get 35 again. Then we square 2 to the power of 32, which is squaring 35 and reducing mod 221. So 2 to the 64 is 120. And then 2 to the power of 128 is 35. Okay, so now that we have all of these, we've got to multiply the relevant ones together. So we need this one. I'll just underline the ones that we need. We need this one. We need this one. 2 to the 64, we need this one. And we need this 2 to the power of 128. Okay, so we've got to multiply these together and then reduce modulo 221. So we'll say 2 to the power of 221 is congruent to 2 times 16 times 120 times 120 times 35, and then it's modulo 221. Okay, so when we reduce this, when we take that product and reduce that, we get 32 mod 221. And since we've done this in terms of the power 221 rather than the power 220, we're supposed to get 2 when 221 is prime. So we'll just say that this is not 2, and hence by Fermat's little theorem, two to one is not prime. Okay, so that completes the proof that 2 to 1 is not prime. Now 2 to 1 is a small enough number that you could just factorize that and find exactly what the factors are, right? And immediately know that it's not prime. But understand the whole point here is that this technique is useful when your number is much larger than 2 to 1. Okay, because you can quickly establish that your number is not prime and therefore has a non-trivial factorization. Okay, next, the converse of Fermat's theorem is false. Okay, so I'll just put Fermat's theorem here so we can look at that. So basically, if P is prime, then you have this congruence, but it doesn't go the other way around. In other words, if you have an A and a P such that P does not divide A, and you find that this congruence holds, well then that does not imply that P is prime. Okay, so the converse does not hold. And I'm going to give you an example here next. So this one says, the converse of Fermat's theorem is false. Illustrate this with 341 in base 2. All right, so let's do this time in terms of 340. So 340 in binary is 1 0 1 0 1 0 1 0 0. Okay, now we interpret this because we've got the 1's place, the 2's place, the 4's place, up to the 2 5 6 place. Okay, so where we have 0 we ignore. So what this says then is that 340 is equal to, let's see, so we don't have any 1's place, 2's place, we do have a 4's place. So 4 plus 16 plus 64 for this place, and then plus 2 5 6. Okay, and so if you add those up, you'll find you get 340. All right, so next, what this says is that 2 to the power of 340 is equal to 2 to the power of 4 times 2 to the power of 16 times 2 to the power of 64 times 2 to the power of 256. Okay, so now we use the technique of repeated squaring again. So 2 to the 4 is 16. 2 to the power of 4 squared is 2 to the power of 8, which is 256. Okay, now this is still less than 340, so we'll keep that as is. 2 to the power of 8 squared is 2 to the power of 16. Okay, so this is this one squared, so 256 squared, but here we should put congruent. Now when we multiply this out, we get 65536. So this is congruent to 64 mod 341. Okay, next, 2 to the power of 32 is congruent to 64 squared, which is 4 mod 341. Okay, next 2 to the power of 64 is congruent to 4 squared, which is 16 mod 341. Two to the power of 128 similarly will give us 256. Okay, 2 to the power of 256 gives us 64 mod 341. Okay, so we take these relevant numbers. So this one, 2 to the power of 16, which is up here, and 2 to the power of 4. And we multiply these together. So 2 to the power of 340 is congruent to 16 times 64 times 16 times 64, and this is congruent to 1 mod 341. Okay, however, so you can see that it satisfies Fermat's theorem, but 341 is equal to 11 times 31. Okay, so it's an example of what we call a pseudo-prime to base 2, because it satisfies Fermat's theorem, but it satisfies the converse of Fermat's theorem, but it's not prime. It's composite there. Okay, so just be aware that the converse of Fermat's theorem is false in general. Okay, nevertheless, you can use several bases. So we can use several bases, e.g. A equals 2, A equals 3, and so on, to give a high chance, let's say, high chance that P is prime. Okay, so for example, 2 to the power of 7 minus 1 congruent to 1 mod 7, and 3 to the power of 7 minus 1 will be congruent to 1 mod 7. Okay, so if you have enough of these, you can gain confidence that the number 7 is probably prime. Okay, we know it's prime, right? But think as if this is a very large number. And that's what a lot of mathematical software does. It'll do a pseudo-primality test, much like this, to tell you that a number is prime, because it's so confident that it's prime via the probabilistic tests that it's basically undocumented to be incorrect. Okay, so that's all for now.